I guess that explains why Kara's out today.
Okay. I even got a couple pictures to show you.
Ooh.
Not those crazy.
All right. Perfect.
Okay. All right. Is it on? Cold?
Yeah. It is.
Really?
Very warm in here. It's so hot.
Yeah, seriously, like we can't let it get this warm. You guys are gonna fall asleep.
I already did that.
You're hilarious.
Freezing cold. I'm not gonna turn on the AC. If you go to not gonna turn it on during summer. 182. I hate this. It's because you're the reason I haven't been here.
Okay, so this whole thing is called solids of revolution, and we're going to basically use calculus to find volumes of stuff, and the stuff is crazy. If you figure right now, like we only have a pretty finite number of volume formulas, like cylinder, sphere, cone, pyramid, whatever, but this kind of like adds a whole new level of things that we can find volumes of. And the way we're going to find a volume is we're going to take a function and we're going to rotate it around usually the x-axis or another horizontal line. It's going to create a solid. So for example, we already have two solids that we know the volume formulas for, but they can also be found with calculus. If you take a diagonal line and I rotate it around the x-axis, do you see that you get a cone? There's no need to use calculus to find the volume of cone because we already have a formula for it, but it's kind of good to just see what kind of shape gets formed. The hardest part, one of the hardest parts about this is visualizing the new shape that gets formed because they're funky. So I thought, well, let me just show you these. If I have a diagonal line and I rotate it, I get a cone. And if I have a horizontal line and I rotate that around the x-axis, I get a cylinder. And what we're going to find is the area, or I'm sorry, the volume within that by using calculus. Let me show you a couple of figures first and then I'll kind of explain how. We're going to take things like this. So, aren't I so fancy? I put this on a Word document. Woo. I found a parabola. So the parabola is x squared plus 1, and they took it from -2 to 2, and they rotated it around the x-axis. So think in your head, what might this look like? Yeah, like hourglass-ish. So here was the finished picture of it.
What?
The black hole.
So you can see, you know, that top parabola got rotated around, and what you have is that figure, and that's what we're going to find the volume of. I think I might have done one more. Just as an example, if you, look at a vase. If this is like the shape of your curve, if I just revolve that around a vertical axis, I get the vase. So that is like how your calculator or whatever finds volume and how computers find volume of stuff. They're actually integrating. We'll get to that in a second. What we're going to do, I didn't explain this very well yesterday with the whole area thing. I kind of like glossed over it. But when we found the area under a curve, whatever that curve is, like from here to here, what we were really doing by taking the top curve minus the bottom is we're integrating like little tiny rectangles. Have you guys talked about this in physics before?
Yeah.
So you talk in physics more about it, that like we're kind of taking the area of one of these little rectangles and we're adding it up an infinite number of times from one side to the other. So these little tiny rectangles have a height. That height is the top curve minus the bottom, right? Like if the height of one of those rectangles would be my top curve minus my bottom curve. That would give me the height. So it's like f of x minus g of x, whatever, if I have two separate curves. And the thickness of one of these rectangles is dx. It's a change in x. It's a little tiny, tiny change in x. And that's really what I'm integrating. I'm adding up rectangles that have this height and a little tiny width. And I'm, God bless you, adding up an infinite number of them from left to right. That's what integrating is doing. We do the same thing here when I talk about volume, except instead of little tiny rectangles, I'm going to add up the area of little tiny circles. Because when I rotate something around the axis, can you kind of imagine that like I'm creating circles? As I rotate something around, I'm creating this like circular shape, even if it's like bumpy. If I could like cut this in the middle and look at it, I'd be looking at circles on either side. They're not going to be the same, have the same radius, but they're still going to be circles. So for me to integrate, or for me to find the volume of this solid, I'm just going to find the area of one of these circles, and I'm going to add it up from left to right. I'm going to integrate it all the way through. And if I have like paper-thin circles, and if I put an infinite number of those paper-thin circles together, I'm creating volume. So I'm just adding up a ton of tiny areas, and it's creating a volume. It's creating some actual three-dimensional space. So to find the area, or to find the volume of one of these solids of revolution, I'm just going to integrate from, I'll say just left to right, the right x and the left x. The area of one of these circles, well, what is the area of a circle? Pi r squared, right? So I'm going to integrate pi r squared, but the r in this case is like the height of my function. So I'm really just using for r the value of the function, and I'm squaring it, times dx, times a little tiny thickness that I can add up forever, or I can add up an infinite number of them between the left, whatever, and the left limit and the right limit, and I'm going to get the volume of the thing. So,
Get the volume of the disc, not of that big, funny, tuber-looking thing.
what's that?
Squared inside, huh?
Well, I didn't need both sets of parentheses, but the squared is only being applied to the f of x, it's not applied to the pi. It's only the function that's getting squared because I'm using the area formula of a circle, pi r squared, r being the function.
Why isn't it just the squaring the integral and having everything inside it? 'Cause
Say it again.
no, I mean, why isn't like the pi and the squared outside of the integral? Why is it inside?
Well, because the squared is going to like the radius of one of these circles, and I'm adding up the infinite number of them. So it's like pi r squared, here's my circle, and I'm adding up a ton of circles. Okay, so I'm integrating a ton of those areas of circles. Now obviously this only applies to volumes of things that are created by rotating something around an axis. Volumes of,
Baseball bats.
right, I was going to say volumes of books or whatever that have all square surfaces aren't going to be the same. That's going to be a whole different thing, and we don't do that. We only do what's called solids of revolution because we take something and we revolved it, and that's what we're going to use. We're going to use that idea that when we revolve, we're making little tiny circles. If I could like cut it up into little tiny circles, and I'm adding up all of those little tiny circles. Okay, I also found, because I'm a geek, that, can you even see it?
Revolution.
It says volume equals the integral from a to b of pi times f of x squared dx. Revolutionary. Get it?
Are you getting that shirt?
No, but there's a whole website called nerdyshirts.com.
Going to it.
Right? There's some really great stuff. Okay, so let's actually try.
Oh.
Wow.
Perfect. It's exactly what I have. Alright, so let's take like
I feel bad for who's gonna watch this. Can't see it at all.
what, the t-shirt?
No, the chalkboard
Oh no!
Why can't they see it?
because of the contrast from the brightness and.
Well, I'm going to turn that off in a second. So Erica can just relax. And Kara.
You keep forgetting about
I know, because Erica sent me an email like, where's the video? She's like calling up my
Oh
height.
yeah, and Corey.
Oh yeah!
Corey's absent? It's taken me 25 minutes to figure that out.
It's been so peaceful. Like this.
It has been. It feels like zen-like. turn this off. If you are geeky, which, come on, we all are, and you go online, you can find some really cool pictures of stuff that they revolve.
I would like to see some videos.
There's actually a cool program called WinPlot made by this guy, like totally for free, where you can take stuff and revolve it, but it's just it's a weird program, I guess that's why it's free. It's kind of like
What was the
Game
moral of that movie?
What?
What was the point of that story?
But you can go online and download this WinPlot program and then rotate stuff yourself and see it, but the program doesn't work that well. Seriously?
Can we do it right now?
Can I rotate
No.
something?
Okay, so when you do this, the first thing we're going to do is draw it. I think, I will tell you, this is one of the things I was worst at. So maybe you won't even need to draw it. I need to draw it to get an idea of what I'm rotating. So e to the x, and I will also tell you not all of these are calculator problems. So we will do a couple that are no calculators. This would be a good no calculator problem because it's not hard to graph or anything. It's not hard to do. So e to the x looks like this, and I'm going to go from 2 to 3. Okay, so it's asking us to rotate the area between the curve y equals e to the x and the x-axis. Oh, I'm supposed to say rotate around the x-axis.
This looks like a tree stump.
Yes, it does. Okay, it's going to tell you what to rotate it around. Today, we're only going to rotate things around the x-axis, and tomorrow, we'll start rotating around lines that aren't the x-axis. So what I do is, since I'm going to rotate this around the x-axis, I like to draw it. What it would look like.
That's not.
You know, everyone knows my skills I don't have any.
They're not there.
They're non-existent. And so if I'm rotating, I think like, okay, this looks like a circle. So I put a little circle there to show myself what it looks like as I rotate it. So yeah, it looks like a tree stump, but like a nice symmetrical tree stump. And all I need to do is integrate from 2 to 3 the area of one of the circles that's formed. If I were to like cut this in half and take a look at the inside of it, I'd be looking at circles. I need to integrate the area of one of those circles. Those circles are all going to have the area of pi r squared, and r is going to be the height of the function. Right now that's pretty easy. The height of this function is just the same, like the radius of this circle is the height of the function is just e to the x. And I should have a dx on the end to represent the width of one of those circles that I'm going to use to add up. Questions so far? Alright, if I'm doing this by hand, I'm going to make it a little easier. And I'm always going to take the pi out to the front so that I can just apply that at the very end. So I've got the integral from 2 to 3 of e to the 2x dx. So if I take out the pi, what is the integral of e to the 2x?
E to the 2x over 2.
Yes. E to the 2x over 2. And that's being evaluated from 2 to 3. So we're going to have pi times e to the 6th over 2 minus e to the 4th over 2.
Yep.
And I guess I'd probably do maybe pi times e to the 6th minus e to the 4th over 2.
Or you could really factor out an e to the 4th if you want to get fancy.
No.
Yeah, but would that really be easier? Okay. Is that alright?
How do you know the radius would be the x?
The radius is literally the radius of the circle. So if I think about when I rotate this, what is the radius of the circle? It's just the height of the function. So since the function is e to the x, that is what the radius is. And realize like that radius is changing. If my radius were here, it's a lot smaller than if it were here. That's why I don't use a constant. That's why I use a function to talk about the radius. Because the radius of the circle is changing as I go through. So when I'm here, my radius is e squared. When I'm here, my radius is e to the 3rd. and in between it's in between e to the second and e to the third. So I use e to the x to represent that like my radius is changing, because this is changing.
Bless you.
Gosh, I'm gonna wipe off that test.
That was gross.
Yeah. Yeah.
How do you know dx is
How do I know dx is what?
the width of the circle?
Just because I'm in terms of x. So I'm going to say it's a little tiny change in x. The width of that circle or whatever is a little tiny change in x. We just represent that with the dx. That's it. Okay, it can get a little bit harder because, let's say we have something like this. Okay, let's rotate around the x-axis the area enclosed by y equals x squared and y equals the square root of x. It's a little bit like yesterday, the one I threw up there at the very end, the x to the third and the cube root of x that I couldn't draw and wasted time on.
From where to where? Or no?
This is just going to be area enclosed by, so if it's area enclosed by, that means you're going to figure out from where to where. Okay, sometimes they tell you from one x to the other x. Sometimes you have to figure out where like that partition is. That's not the only reason why this is weird. So let's draw it. Can you guys see these markers? Can you see? Mac, are you being serious? All right, x squared. This is the square root of x, and this is x squared. I'm only going to draw the one side of them because I know that that's where they intersect.
Fish.
Okay. Watch what happens with this. Well, they're going to have an intersection point. I do need to find the intersection point. Where will it be? 1, 1, right? So that intersection point is going to be easy, and the other one is also easy because it's the origin. Sometimes you'd actually need to go find that point of intersection if they're just telling you the area enclosed. If I draw this rotation around the x-axis, what happens when I rotate? What's different?
It's hollow.
It's hollow. It's got space inside. The other one was just this. So when I rotated it, whatever, it had no space. It was just like a whole solid thing. Well, this one's hollow. If I kind of look at it, I've got like this outermost circle, and I've also got an innermost circle because it's going to be all hollowed out on the inside. The only change you need to make is that it's going to be pi r squared of the outermost
It's like a
circle
bowl with the ball keeps
minus
getting
pi r
smaller.
squared of the innermost circle. Because I want to take out that middle part. Can you kind of picture what it's going to look like or no?
Of course.
Yeah.
Flower.
I don't know, it's kind of like coming in like this,
Flower.
I guess. So, okay, so it's going to look like this. We're going to have the integral of pi r squared of the outer circle minus pi r squared of the inner circle. I'm still going to go from 0 to 1. So that left to right doesn't change because like the curves didn't change. I got the same one on the outside as I do on the inside. So it's important to know what curve was on top. What radius makes up the outer circle? Yeah, draw yourself maybe that circle and be like, all right, how big is that radius? Like go to the square root of x, that's my outermost radius or my outermost function, minus the radius of the innermost function, which is x squared. And technically I've got a dx after the whole thing. The biggest mistake people make with this problem, and it happened a lot last year, and maybe I did something weird with it, you cannot distribute this, like you can't make this root x minus x squared quantity squared. Okay, it's not going to be that. It's got to be pi r squared minus pi r squared. The radiuses or radii get squared by themselves. You can't combine it into one big thing. See what I mean? Just got to be pi r squared minus pi r squared. So this is like its own little thing, and that's its own little thing. The pi's can come out, so this can be pi out here, and take them both away, that's fine. But both radii need to be squared separately. So you can put this in your calculator. If it were me, I would put in pi times, and then FNINT. I would just put in x minus x to the 4th, because the less like parentheses and stuff you have, the easier. So I would probably simplify this and simplify that. Comma x, comma 0, comma 1. I don't know if I wrote the answer down. No, I didn't. Whatever you get, you get. This is called the washer method. If you ever are looking in a book, this would be integration by washers, because what they think is, when you rotate this, what is that kind of look like? You have like washers, because you don't have, yeah, you don't have full circles. You've got the middle taken out of the circle, so they call it the washer method. The what? Flower, there you go.
0.3.
I didn't even do the answer.
Yeah.
Okay, we are gonna have to do a couple of these for homework. Come on, you like hardly even have that much.
0.3
Yeah, but it's
pi.
Christmas.
What's 0.3 pi?
I'm not gonna be home until midnight.
Oh, yeah.
I'm gonna be out all night because PJ's is gonna be packed.
Why is
It
it
really is
that?
important that you try a couple. It's just
So
gonna get
many
harder
robotics people
tomorrow.
are gonna go, and there's probably a sports game tonight.
It won't be that bad. Homework, go to PJ, guys. If not, you fail.
Do you think Chris will